it is. So essentially, this shouldn't be a surprise to anyone here. I look at the input layer as one random variable, high-dimensional random variable. So think of pixels of an image, for example. This is multi-millions of variables, millions of binary variables, even if you think about it. So I call it X, just the input variable, the whole layer. And then usually this is a high entropy variable in the sense that there's a lot of randomness there. So think about X as a high entropy random variable. Usually the label Y is much simpler. I mean, at least in the classical supervised learning scenario, Y can be 1 bit, okay, or a few bits, okay? So essentially what you are given is a sample of the joint distribution of X and Y, which is what I call data, or training data. And then what the network is doing is essentially moving it through a cascade of hidden layers. This is the first hidden layer, the second hidden layer, and so on, in a way which is actually a Markov chain. I mean, each layer can be calculated only from the previous one. So this is a Markov chain of successive representations. And eventually, the last layer, which I consider actually to be very important in this story, is generating another random variable which is supposed to be as close as possible to the original Y, which I call Y hat. So if my training works well, this some sort of refinement of X through the layers should eventually lead to good prediction of Y, but that's not exactly Y, of course, that's why I call it Y hat. So, and of course, what's actually going on in these layers is a mystery. I mean, this is the big question, how this particular succession, of course, you all know what these neurons are, the nonlinearities of dot products of weights with the previous layer, but in a sense, these variables are just what I call X hat in the bottleneck framework. Essentially, these are some sort of an internal representation, which actually is made out of a succession of many layers of several internal representations like this. Each one is just calculated from the previous one. And this is supposed to be some sort of a relevant representation of the prediction. OK, so this is, to me, what we call a bottleneck problem. I want to squeeze out of X everything I can, except the thing that is actually relevant for Y. And so in some sense, I want to compress X. I'll show you exactly in what sense. Such that only through this process, through these layers, only the information that X shares with Y is stayed out and eventually floated out in one linear classifier at the end. Okay? So that's deep learning for me. The question is how it happens. So I just want very quickly to, if you give me a few more minutes than 45 minutes, it'll be even nicer. But this is the two functions that I hope all of you know, but I just want to remind you. One of them is the famous scale divergence, or cross entropy, or information divergence, many different names. It's essentially the average log likelihood ratio of two distributions. Average with respect to one of them, so it's not a symmetric quantity. And it's not negative. It's 0 exactly when they are equal almost everywhere. And the mutual information, this is an important function. I'm going to use it again and again. It has many good properties. I don't have time to review all of them. The second one is the mutual information. The mutual information essentially is the KL divergence between the joint distribution of the variables and the product of the marginals. And it's 0, even only if they're independent. And it can be written in various ways. The important way for me here is the entropy of the variable X minus the conditional entropy of the variable X given Y, which is essentially how much of the uncertainty of the variable X is removed when I know Y. Now remember that X is given, so I don't have any effect on the entropy of X in most cases, but I do have, of course, an effect on the conditional, and we'll talk about it. There are two properties of the mutual information I want you all to remember. One of them is what we call the data processing inequality. So essentially, when you move along a Markov chain, X, Y, Z, and so on, the mutual information only decreases, which means that the mutual information between X and Y cannot be smaller than the mutual information between X and Z cannot be larger than the mutual information between X and Y, and so on. So if you move along the layers of a network, mutual information about the input variable can only decrease. And so it is about the mutual information about Y also. And the other thing which is really important about mutual information is that it is invariant with respect to reparameterization. So if I do some sort of a permutation or any invertible function, whether it's continuous variable or discrete variable, doesn't matter. The mutual information doesn't change. This is, in some sense, a special case of this. But so mutual information can have the same value. Again, if you think about layers and networks, even if I shuffle or permute the variables in the layers completely in a crazy way, as long as it's an invertible function. Okay. So I think the information bottleneck was already introduced, but just one slide about it. So essentially, there is a classical notion in statistics called minimal sufficient statistic. You talked a lot about minimality and sufficiency, and just briefly mention it. Essentially, if using the data processing inequality, DPI, you can see that a statistic is called sufficient if it preserves all the information about the parameter, in our case, about the label. So S of X is a sufficient statistics of X with respect to Y if the mutual information between S and Y is the same as as X with Y. It's a minimal sufficient statistic if it's the minimal, it preserves the minimum information between to X among all the variables that are sufficient statistics. So that's a variational or practical definition of a minimal sufficient statistic. And then we relaxed it in 99 and called it, okay, let's say that I don't have all the mutual information, I preserve as much as I can of the mutual information, and then you have this variational problem. Minimize the mutual information on X, subject to a constraint on the mutual information of Y. I noticed by looking at Alessandro's slides that my beta is actually the inverse of his beta. So this is 0 when you have no information about Y, and it goes to infinite when you have all the information about Y, okay? So, and this is just like 1 over temperature in statistical physics. And it's, of course, can be formulated as some sort of array distortion problem with a very specific distortion function, which is precisely the KL divergence between how well you predict Y from the original X versus how well you predict Y from any compression of X or any statistic of X. And if it's a perfect sufficient statistic, the distortion is 0. Otherwise, this distortion is directly related to the mutual information between Y and X hat. So if you go back to the neural networks, what we have are 2 lines of inequalities. So what I'm going to call the information paths of the network. Essentially, I want now to calculate the mutual information between each of the layers. Later on, I'm going to call them T instead of H, but it's the same thing. So between the layer in the input and the layer and the output. And I know that these 2 chains of values are monotonically decreasing because of data processing inequality again. So the mutual information only goes down, its maximum with respect to X goes down, and with respect to Y goes down. Now, notice that each one of those layers is actually inducing a partition of the input. If you think about the values that the hidden layers can take, there's a probability which can be hard partition or soft partition, depending how you interpret the softness of the units. If it's hard units like sines, then it's a hard partition. If it's something like a sigmoid, then it's a soft partition, if you interpret it probabilistically. But essentially, any layer is really inducing a partition of the input, which is actually very important. I'm going to talk a lot about those partitions. And in the language of information theory, we actually can call it a successive refinement of the relevant information. I'm inducing a code which is getting coarser and coarser when I move through the layers. It starts with very fine code at the input layer, and the layers that follow it actually refine the information in some sense. So another way of thinking about it before this theorem is to think about the input as being encoded by a layer, let's say this Ti. So, and I call the map from the input to the layer the encoder of the layer. And from the layer to the output, I call the decoder of the layer. And actually, so here comes a recent result, which I found quite important. So essentially, I argue that for large enough problems, which means that when X is large enough, such that we can actually talk about typical X's, which means I'm going to confine myself to what in information theory we call typical sequences or typical variables. So if the variable becomes very large, almost all, in some very specific sense, of the values of X are going to be dominated and equally probable completely by the entropy of the source X. This is true for information sources, information theory, for those of you who know a little bit about it. It's also true for most of our big learning problems, like image recognition or whatever it is. We are talking for a long time now about large-scale problems. And that's really the beauty of it, because now I can use all the asymptotics of information theory in a way that is completely rigorous and completely okay. So essentially, what my argument is that when you talk about such large neural network, the sample complexity, which is how many examples you need in order to achieve a certain accuracy in generalization, is completely determined asymptotically by the value of the mutual information of the encoder, which means how much information there is between X and the hidden layer for the last hidden layer of the network. And the accuracy or the generalization error, the precision, the probability of making an error on a new sample is completely determined by the value of the mutual information between the layer and the input, the desired input. Not the true input, but output, the desired output Y. So these two quantities, in some sense, are sufficient to characterize the two main things we care about: number of examples and precision for large enough data. So that's a very bold statement. I know that none of you believe it at this point. So I'm actually going to try to convince you this is true and then show you why it's so important. So before I show some mathematics, I want to show you a nice movie. I know it's early in the morning, you're still asleep. Anyway, so essentially I'm going to play quite a lot of this kind of movies. I want you to understand them. So this is what I call the information plane. The information plane is the information in bits. Actually, it's not in bits here, it's in bits in LAN instead of log, so never mind that. It's in bits of the layer, each layer is a whole random variable, the whole layer. Yeah. Forget about neurons, they're not important. It's layer. So the whole layer to the input variable, this is ITX, and this is the whole layer to the output variable. Since this is a binary problem, this can get to 1 bit, which is in this unit 0.7, and this can get to 12 bits, which in this unit is 8 something. Never mind. This is a small problem. I'll show you exactly what the network is, and then I'll argue this is a very general picture. And what I want to show you, so those little spheres, essentially, this belongs to the last hidden layer. This is the one before the hidden layer, and so on. Each color is a different layer in the network. And there are 50 different random repetitions of the same problem with different initial conditions and different order of the examples. So there's some stochasticity here, which is due to the initial conditions of the network and order of the training examples. And what you see here are the initial conditions. So you see that the high point here, this is the input layer, or the first hidden layer. This preserves essentially all the information about the input and all the information about the output. Of course, I didn't do anything. But when you start with random initial conditions, the information drops down very quickly, and the last hidden layer essentially has very little information, both about the input and the output. So I want to show you how these things evolve when you train the network with stochastic gradient descent. So look at it, it's quite nice. So essentially what you see is that the layers come up as you expect. I mean, the information about the label is increased. And then at this point, they somehow slow down and start to do this very funny thing. They move to the up and to the right, left, which means they compress the representation in some sense. They forget the input. And eventually, you see the number of epochs. It's essentially running. Eventually, they converge. Believe me, they don't really converge here. But you see that even that the last hidden layer still is stuck already in one place, the previous layer still moved to the left. Let me show it again, because probably you haven't seen all the nice features of this. So again, the first phase is coming up very quickly. This happened within 350-something iterations. From this point, something very strange happens. They move slowly and together. These are 50 different initial conditions of the network. That's why you see all these clouds. And eventually, they move to the left. So just to make this clearer, I'll show you the average over these 50 networks. So, and just tracing it. So essentially, okay, so this is the first phase, 300-something. And then this very, very slow convergence to the left. Okay, this is real neural network, TensorFlow, using no regularization, no specification, nothing, no dropout, nothing of these tricks. And essentially, you see that most of the epochs of these 4,000 epochs, about essentially 350, you get to this point, more or less. You see, you increase rather quickly. And then from here starts very, very slow motion upward and left of all the layers. This is what I call the compression phase of the network. And the main part of this talk is really to convince you, first of all, this is a very general and very real phenomena, and then convince you that it's actually an extremely useful phenomena. This is really, in my opinion, the important part of the SGD algorithm, because it's not really fitting the data, forget about it. Even with very small data, you get to this point, very small data. It's this part, the compression and the keeping the information high, which is so useful for the network. So let me go back to the theory. So I hope that some of you know something about PAC learning and learning theory. And usually, you should be familiar with what I call the old type of generalization bounds, which is essentially that the generalization error, probability of error outside my training data, is bounded, or some power of it, usually square, is bounded by the log of the hypothesis class cardinality, which essentially, for finite cardinality, is simply what's called the cardinality bound. But for any general cardinality, or general class, general hypothesis class, we usually use what we call epsilon cover of the class. We actually sample it on a grid, such that all the hypotheses, there are epsilon close to each other, and then we can settle with finite cover of the hypothesis class, divided by the number of examples up to some constant, I don't care about the constant, plus a small number, which actually for typical large problems is negligible completely, which has to do with the confidence, okay? So this is, everybody who took the first course in learning theory knows about these bounds. And then usually, what we have is some sort like the VC dimension or other dimensionalities of the class that essentially tell us that the cardinality of an epsilon cover of the class scales like 1 over epsilon to some dimension. This is that if I plug this here, I get the D over M as the main factor, which is really telling me as long as the number, for example, is smaller than the dimension of the class, you are not generalizing. Once it goes above it, you start to generalize, either like 1 over square root of m or like 1 over some other power of m. That's classical. The problem is, as I'm sure you all know, but maybe don't appreciate, is that, thank you, Klaus, for this mail. Maybe you don't know, but the deep neural networks these bounds are useless for deep learning. They don't work. Why they are useless? And actually, they get even worse when you show me that the network can express very complicated functions. I mean, all those are complicated and very, very sophisticated expressivity bounds essentially push the dimension higher. So this dimension is now in orders of the millions or tens of millions, and I have hundreds of thousands of examples and actually generalize very well. So obviously, this doesn't explain anything. And they just move by many people in the wrong direction. So I suggest a different bound. I call it the input compression bound. It's quite new. It's actually surprisingly, it's related to many things that people know for a long time, like nearest neighbors and like many other partitions. So instead of focusing on the hypothesis class, which I actually think is completely an irrelevant notion for deep learning, think about what happens to the input. Now, I already told you that the layers induce partition of the inputs. So I'm going to quantify this partition by how homogeneous they are with respect to the label. So if I'm actually managed somehow to compress my input into cells or cover my input space with cells which are more or less homogeneous with respect to the generalization or with respect to the label, then I'm doing a much finer job in terms of, so imagine that I actually cover the space of inputs X. In the case of images, let's say it's all the possible images that you care about. It's a very big space, and I cover it with spheres which are essentially groups of images, clusters of images if you want. It can be a soft or hard partition. And essentially what I'm saying, that then I can replace the cardinality of the hypothesis class, let's say the Boolean function, just for simplicity, it moves from 2 to the cardinality of X, which is all the Boolean functions from X, to 2 to the cardinality of the partition. Okay? Because essentially now I need, if I manage to epsilon cover my input, then essentially the input moves from x to t to epsilon in terms of number of labels that I really need. I need essentially 1 label per partition. So it looks okay. So this is an exponential decrease, but it's okay. But notice that if I said, okay, so now there are 2 questions. But first of all, how do I make sure that the partition that I get is indeed homogeneous with respect to the labels? So this requires some sort of a distortion function. I mean, I compress it just like in rate distortion theory. I want my grid or my code book or my partition to have closed small distortion. The only thing I'm saying is that the distortion that we need to use is actually, if I use this information bottleneck distortion, it's actually bounding the L1 distortion, which means that if this is going to be an epsilon partition with respect to this, it's also going to be an epsilon partition with respect to this, the same topology. And therefore, since the information bottleneck distortion average is precisely related to the mutual information in the representation, this is minimizing this is equivalent to maximizing the mutual information on the output. Okay, so that's very nice, although not surprising to anyone. But now I'm going to play information theory and essentially tell you that, okay, so you know what the size of this partition for typical sets. I mean, so if x is large, the size of x is 2 to the entropy of x. If you're not sure about that, come to me later. And then if it's a typical partition, the average size of each partition is 2 to the conditional entropy of x given t. This is the same trick exactly used in the channel coding theorem and in the rate distortion theory. So you should be familiar with it. But notice then that the size of the partition is simply the ratio of these 2 things, which is exactly 2 to the information between x and t. Okay? So I can plug the cardinality of the partition is actually exponential in the mutual information between x and the partition, which is exactly what I call the compression. So plugging this is a double exponent, yeah? So h moves from 2 to the t, which is 2 to the I. So this is 2 to the 2 to the I. You plug it here in the log, and you get still an exponent. Okay, so that's quite remarkable in the sense that if this is actually going down, as you actually saw in the simulations, it's actually moving to the left of my plan, then k bits of compression of x are equivalent to 2 to the k factor of 2 to the k training examples. So this is a much more powerful bound. I mean, if I manage to compress the representation, it's just like multiplying the number of training examples by 2 to the number of bits of compression. So when you see this, you understand, okay, maybe this stochastic gradient descent is not so stupid. After all, it's actually allowing me to lose a factor, an exponential factor of examples in terms of improvement. So maybe this is, or at least this is what I claim, is the reason the networks don't overfit. Because during this compression, they essentially reduce the dimensionality by a factor 2 to the minus k. And any bit I can compress is improving my generalization as if I reduce the dimensionality of the problem by an exponential factor in the number of compressed bits. Okay, so that's the first part. Now, remember that again, I think that Alessandro more or less said it. Maybe he didn't show you this picture. So, of course, the problem is that I need, for this to be true, my partition has to be an epsilon partition in terms of generalization error. But I don't know the generalization error. I have a sample. If I have a sample, I need to bound the distortion with which I am doing this epsilon cover with respect to the empirical distortion. And as I showed you already, this distortion is directly related to the empirical mutual information. So I need a bound on the difference between the true mutual information on Y and the empirical mutual information which I get from a finite sample. This is something we derived actually a long time ago with Ohad Shamir and Sivan Sabato in 2008, and actually a very standard uniform convergence bound. The difference between this scales like the square root of the number of partitions, which is 2 to the I, as I just showed you, divided by the number of examples, multiplied by the cardinality of Y, which is 2. Okay, I don't care about this. So this is nice because it's actually telling me, look, in the information plan, remember the information about the input versus the information about the output, there are essentially there's a line here, this black line, which is like a rate distortion function. This is the information bottleneck bound. Just tell me, there are no representations, there are no partitions about this line. This is the best you can do. This is my optimality bound. Now, if you look at the neural network, like what I did before, it's some sort of a line actually goes like this, behind this black line. When I train the network, when I showed you this movie, all the points come up, and I claim that they actually eventually converge to this optimal bound. But this optimal bound is only if I actually know the true distribution of x and y. But if I don't, I have only a sample, I'm actually fitting this red bound. This red bound is exactly this finite sample bound, and you see because the cardinality grows when I move in this direction, because the information goes smaller, it has a maximum somewhere, and then it dramatically drops. So this is what I actually know about the uniformity of the partition with respect to the label. So obviously, it seems obvious that the network should push the last layer to be near the maximum of the red curve. And then you suffer the minimal loss. There are two losses in terms of two imprecisions in this argument. One of them is what I call the compression loss, which is what I will induce by any compression which is lossy. This is the first part. And then there is the finite sample loss, which is the difference between the red and the black. And I want both of them to be small in order for my bound to be worth anything. So remember that, and essentially, OK, I have to run up. How much time do I have? I don't know. You don't stop, I continue. That's all right. So essentially, I want to show you what I owe you two different important things. Actually, what actually happened in different large problems. And I need to explain what happened with finite samples. I need to explain what is the benefit of the hidden layers. And then we'll see. Then you can talk. OK, so essentially, these are those traces that I showed you before in one image. The color is the number of epochs. Dark blue or black is small number of epochs. Red and yellow is very large number of epochs. And you see the traces of the layers. This is the first hidden layer actually just moves to the left a little bit at the end. This is the last hidden layer, which I claim is so important. So it climbs up. This green line is what I call the gradient phase transition. I'll explain it in a second. And then they slowly moved up. That's essentially the picture you see. This is with 80% of the training data. This is with 40% of the training data. And this is with 5%. So this is overtrained in some sense. I have enough training data. And this is undertrained. And what you see here is that until the compression, more or less the same thing, 5% and 80% gives you essentially the same convergence in the same line. But the compression is very different. Here I'm actually losing information. So this is what you usually call overfitting. But it's really not exactly overfitting. You actually simplify the model. But since you cannot guarantee the homogeneity of the partition with respect to the label, you lose information by compression. So early stopping is a good idea here. Notice that eventually this point is going to determine how well you do, because this is what you're going to do. So this is quite poor. Here it's quite good. The other thing I'm going to argue is that they actually converge to the optimal information bottleneck curve at the end. So I want to, first of all, of course, so I want to show you another movie. I want to show you the same movie about the information plane, that now this time with the generalization and training error. OK, so this is here. So essentially, what I want you to notice is that this is the training and generalization error, a test error. And you see that they, well, exactly the interesting part is covered. You see that right here, in this place where they condense together, the error essentially flattens. It saturates, and then you get very, very slow improvement in the error. There's no overfitting, at least not in this problem. You see that the training and generalization simply follow each other. But there's still improvement, and most of the action, as far as I call it, this compression, happens when the error is very small. Essentially, you fit the data. According to all the theories you did empirical risk minimization, you should be fine. But you still keep on training. The data is already, the error is very small already, and you still improve the generalization. And improve generalization because of what I told you before. I mean, you compress the representation. Now, so essentially, something quite interesting happens when there's this knee in the training error. And this knee, of course, what it does is essentially affecting the gradient. So here is the most important slide of my talk. This is the properties of the stochastic gradient itself. So remember, I'm doing plain vanilla stochastic gradient, nothing fancy about it. And what you see here, this is the network, by the way, I was playing with so far. It's a small problem, 12 inputs, and a very nice Eiffel Tower-like layers. And you can, of course, argue this is very special. OK, I'll show you immediately it's not very special. And what you see here are the mean of the gradient per weight and the standard deviation of the gradient per weight in the whole layer. So the red is the lower layer, the first hidden layer, the second hidden layer, and so on and so forth. So the color code is according to the layers. And you see here is the number of the function of epochs. Everyone can calculate this thing. Nobody did it before for some reason. And you see that it starts at the very early epochs. Notice this is a log scale. Okay? So at the early epochs, the mean is 3 orders of magnitude larger than the standard deviation, which means that it's a very high signal-to-noise gradient, very clean gradient. And this is pushing you, indeed, very quickly in the information plane high. And then at some point, around 300 and something epochs, the error saturates. When the error saturates, the gradients become very noisy. Actually, it is mini batches that we all play with in the stochastic gradient descent, which is causing these fluctuations. And these fluctuations, indeed, pull the standard deviation to be orders of magnitude above the mean. So in this phase, which is most of the epochs, from 300 to 9,000, which is what I call the low signal-to-noise gradient. I mean, the gradient is extremely noisy. Notice something quite remarkable. Towards the convergence, the difference between the red and the red and the blue and so on for each layer is essentially constant. This is something I noticed only by looking at the simulations, which means that the difference in the log of the mean and the log of the standard deviation is constant, which is the log signal-to-noise ratio. And the log signal-to-noise ratio is directly related to the capacity of the information between the layer and the output. So this is the back-propagated gradient, and what you see here is a saturation of the capacity. And of course, this is precisely what you know, because all the layers in this point convey all the mutual information about the output. So this is a very nice sanity check. There is another interesting thing, that you see that the noise is higher for the lower, noise per weight, is higher for the lower layers, and is getting lower for the higher layers. You can think that this is due to the width of the layers. It has nothing to do with the width we've played. It has to do with the fact that they are further away from the output. So this is higher noise because the noise is accumulated when you back-propagate the gradient through the layer. OK, so this is going to, again, be consistent again with my last chapter, which, OK, first of all, you should, and you're rightly asking, as all the reviewers, is this a general phenomenon? So here's an entirely different rule, entirely different network, also a small network. This is the information plane. It looks slightly different. It's much faster convergence. This is a committee machine, by the way, for those of you who know what it is. And you see, again, very fast climb. And then in this case, actually very fast compression. Move to the left. Here is the gradient picture again. You see the same type of phase transition. High signal to noise, low signal to noise. And the same ratio of gradients, which is constant at the end. If you don't believe that this is general enough, here is a large problem. It's called the MNIST data. Maybe you heard about it. And this is exactly the same picture. This is actually for one single network. You say I don't need to average. It's such a big network that it's self-averaging very nicely. And this is for averaged over 15 networks. And you see exactly the same picture qualitatively. Very quick climb up, and then very slow compression. And notice that the layers get stuck at some places. I mean, it's red here. It gets more or less to this point, and then it slows down. And essentially, you see this difference between the yellow, which is 10,000 epochs, and right next to it, it's red, which is here, which means that essentially nothing changes right next to this convergence. So something stops the compression of the hidden layers. So I want to understand that. So first of all, OK, this is, by the way, the gradient picture for the MNIST data. How much time do I have? No time. So just this last picture, OK? So having said what I said so far, we want to understand why the hidden layers help you. And So this is the same problem, this toy problem that I mentioned before with the 6 hidden layers and 12 inputs, which, by the way, all the mutual information calculated are simply estimated directly by counting. I have 4,096 patterns. I simply put all of them and count the configurations of the hidden layers directly. There's no problem of estimating this mutual information. Anybody can do this. Actually, we do exactly the same for the NIST data. It's just 65,000 patterns and not 4,000, but it's the same idea exactly. So I'm not playing any tricks with sophisticated mutual information estimation. Now, this is the same problem trained with 1 hidden layer, 2 hidden layers, 3, 4, 5, 6. There's one thing I want you to notice. With 1 hidden layer, essentially it takes forever to get to a good generalization, to high information about the label. And you see this, of course, by the color. It's all in the yellow and red, and even here I'm not quite converged yet. With 6 hidden layers, essentially everything is blue. It's here. Very, very quickly I converge to very good representations. Yes?
Do you have the same number of parameters in the 1 hidden layer? And
it really doesn't matter, but yes, I can.
Okay.
This is 12 plus 1. It's 12 plus, the last hidden layer is actually 2 layers, 2 neurons. It's very small here. And this is actually all the full-blown 6 layers that I showed you, 10, 8, 6, 4, 2, and essentially the 1. So essentially, there are many more parameters here, a lot more, but you see the convergence is exponentially faster. Why is that? No, but there are less parameters. There are much fewer parameters here than here. Yeah, this is the full-blown hidden network, and this is a very simple one. But I don't know how to keep the number constant when I increase the number of layers. Yeah, I can. Yeah, okay. Yeah, it's a good question, but it doesn't matter. I mean, the effect is different. Yes, I have many experiments. I simply don't have time to show you all of them. We played with uniform widths. We played with wide widths wider than the input in the middle, and so many different things. You always see this type of picture. Believe me. I mean, I can show you the paper. Okay. No, it's all right. So I simply don't have time. But this is quite a dramatic effect. You see, so I actually argue that it's a computational benefit. It's really converging faster to good solution. And here is, by the way, the reason. Again, I'm sorry if I'm taking a few more seconds. So stochastic gradient descent is governed by this Langevin type of equation. The weights per this k is the layer index. The weights change according to minus the gradient of the error plus noise. Now, this noise scales, as I said, with the layer. So in my case, I call it beta to the -1 because it's going to be directly related to the beta of the bottleneck. We'll see in a minute. And I assume that the Gaussian noise, which is not a bad assumption for this type of backpropagating error, it's a sum of many random variables. Now, this type of equation, this Langevin equation, this diffusion equation, if you want, we know that it's converging for a long time, for 150 years, more or less, that this is converging into a maximum entropy solution with respect to the gradient, to the error. So this is what we call relaxation, relaxed to the equilibrium or stationary distribution of this equation, which is a maximum entropy distribution exponential in the error. What is striking is that the relaxation time is exponential in the amount of compression, in the amount of entropy increase. If you all know something about diffusion, I hope. So diffusion, let's say, starts with a delta function and increases like a Gaussian with a width that grows like square root of number of steps. Okay? And the entropy of a Gaussian, as you may know, is the log of the variance, or log of the standard deviation, actually. So the entropy increase in diffusion is exponential, is logarithmic in the number of steps, which means that the number of steps is exponential in the entropy decrease. It's not always the case. There are all sorts of anomalous diffusions. There are very few things that stop diffusion. One of them, by the way, is what we call critical slowing down. I mean, when you reach a phase transition, you suddenly stop. And I believe that some of those networks are actually related to this. So essentially, the reason why the layers actually help us is that because instead of doing one very slow diffusion from the beginning to the end, I'm putting in between layers, all of them go through diffusion because the noise is added to all the layers. You know, it's just like putting more engines in a train. Essentially, it's boost every layer is now compressed only from the previous one. So if I compress one of them because of this Markov chain, they all move. So essentially, instead of having one exponent of the sum of all the compressions, I have a sum of exponents. Each one of them is compressed in parallel in some sense. So this is an exponential boost in the number of training data, in the training epochs. So this is more or less the explanation. Of course, we need a more rigorous argument. I'll just finish with this. This is where the layers converge to in the information plane after many, many training. And the blue line is the information bottleneck bound for this small problem that I know how to calculate exactly. And you see, I think, quite convincingly, the spread is over these 50 repetitions of the experiment, that they converge convincingly to the bound. Not only that, a simple sanity check tells me that if I'm right, and the story is that essentially this maximum entropy relaxation that I mentioned is actually increasing the conditional entropy of the partition. So essentially, by randomizing the weights, I'm increasing the conditional entropy, and that's why I compress, because increasing this is minimizing this. So the maximum entropy, the noise, is really wiping out, in some sense, the irrelevant information and compresses the representation. Now, the beta that you see here is completely consistent with the beta that I see of the convergence of the Lesberg. So the fact that I get more noise in the lower levels is actually explaining why I get this very nice convergence in different beta along the curve. So this was some sort of a consistency check, which I found quite remarkable. The last question I'm just going to pose is, where do these layers converge to? So what you see here is a nice picture, but this time the color is in terms of the training data size, not in terms of the epochs. And this is the final convergence of the layers. So this is the first hidden layer, the second hidden layer, and so on. And you see that it's remarkably consistent. Actually, the layers don't all compress together, they compress partially. They stop at some point. So essentially what I argue is that it's not, so far I talked about the layer as some sort of a scaffolding, essentially, which is just pushing the last layer during this relaxation. But in fact, they actually capture some very interesting features of the data. And now I can give you a whole different talk about what happened in symmetric problems, for example, where you have symmetry group underneath. This is related to your talk, but I don't have time for that. But I do want to, okay, there's actually a lot I can say about it. But the nice thing is that we actually, in some cases, I can calculate where are these layers going to be. So you can solve analytically, if you want. If there is symmetry in the data, then I know that this diffusion is going to get stuck in some places, which, due to phase transitions in the partition. Phase transitions here mean that essentially the partition split or changes topology. Those clusters split or things like this. So essentially, we have some sort of bifurcation diagram which really explains the position of the layer, but I really have to stop, so let me finish here. Since the information plane provides very nice visualization of deep learning, the advantage of the layer is mostly computational due to this exponential relaxation, and there are many good questions to ask, and we are still working on it. Thank you very much.
Yeah, I get the micro. We looked into these deep neural networks, and always were wondering why the networks know to build the simple features. For CNNs, it would be edge detectors at the lower layers. Who tells the network this? I think perhaps you have an explanation for this, because with the compression, probably you can explain this, the lower layer from the input can compress more. Would this be the reason why lower layers learn some more simple
That's right.
features?
So you saw that the layers lie on this curve, and the more compressed they are, the more they forget the input, in some sense. Actually, I told you several times that the intuition is that the noise is actually wiping out the irrelevant parts of the inputs. And that's why it's compressed. I forget everything that I don't want to remember. But it's not, it's happening in stages. That's exactly as you said. I mean, the lower layers forget very little. And so what they forget is actually some sort of a new feature. And if there are symmetries or other reasons to believe that this feature is important, this layer This is why, by the way, the lower layers are much less specific, more general. They move, let's say, take all the object recognition problems and then you do face recognition. The lower layers are going to be shared by a lot of other problems. The higher layers are going to be more specific. And we actually see it. I mean, there's another movie I really wanted to show. This is, by the way, the capacity of the relevant information as a function of the training. And the blue is relevant. The red is irrelevant. And you see how nicely, essentially, so the relevant channel in this case is 4. And you see that this is the information plane again. This is the last layer. And you see that it moves up. And then during the compression, the irrelevant part, which is the yellow, is essentially wiped down. But it happens layer by layer. And eventually, the whole network conveys only the relevant channel. So indeed, that's what happens. The noise is added to the irrelevant channels. The signal-to-noise ratio goes down. Signal-to-noise ratio goes down. The capacity decreases. And you get less information in all the irrelevant channels. And there's actually another movie that I don't have to show, which is exactly answering your question. With the layers, the irrelevant part goes down, but not completely. So the hidden layers, indeed, the lower layers indeed capture a lot of irrelevant information, which is actually relevant for other problems. And we actually see it very nicely in this simulation. Yes, please.
Yeah.
I know that I'm over time, but I'm sorry.
It's fine. It's
Last
fine with
day.
me.
Yeah.
So, very nice talk. You said, so I'm not sure if what we saw was specific to stochastic gradient descent or just training in general.
I need the noise.
You need noise.
I need
Where
noise.
was that? Why did you? I mean, I didn't see that you.
Well, the whole process of entropy increase is essentially a noisy relaxation problem. So I think that the noise in the stochastic gradient descent, maybe not exactly what as the originators, the inventors intended, is not for avoiding local minima. I really don't believe this is the problem in general. It's for compressing the representation. And it's done. By the way, so of course we played with the batch size, the mini batch size. It changes the stochastic gradient picture. So if you take a smaller batch size, you get higher stochasticity, larger batch size, smaller stochasticity. So the phase transition in terms of the gradients shifts. But the picture in the information plane hardly changes, which means that even with very large batches, you still get the same compression. It just takes longer time. So there's an optimum batch size for that.
It's not one, you mean?
It's not one. No.
Tali, what about recurrent networks?
Okay, a good question. Of course, still have a few years to work, but it's okay. As long as the recurrent connections are within the layers, nothing changes. I mean, it's the same mark. I don't use any assumption about the structure. By the way, the MNIST data was done with convolution neural networks, with ReLU's nonlinearities, with Adams, I don't know, all sorts of tricks, and the same picture again. So I don't believe that anything like this. But of course, recurrent and feedback connections are going to destroy my Markovianity assumption. But it can be extremely interesting to look at the information plane for recurrent networks. So you are not going to have this monotonic decreasing. You're going to have some more interesting picture. But I think that as long as the net information flow is feed forward, some can go back. As we do have in our brain, in most of the more or less layered systems, vision, auditory, whatever, I do believe that this is a way of analyzing it at least. And we're actually thinking about it, but I'll come back to this in some other meeting.
Okay. Tali, there was some work by Grégoire, in fact, it's a 2011 paper, so where we find similar things. In fact, we didn't look at the dynamics of the training process, but we assumed that the model was trained, and we tried to understand what it actually does. And what you find is exactly what you're describing. So you find that the model, if you consider layer after layer after layer, it compresses the data, and it denoises it at the same time. So it's exactly the same.
Right, the partition becomes coarser and coarser.
Yes.
It becomes less homogeneous because it's a larger partition, and as long as you manage to keep it homogeneous with respect to the label, you're fine. That's the story. Nothing else. And everything else are details which are, by the way, the fact that all the neurons essentially converge to very similar information is very bad news. It actually has a mixed message to neuroscientists. One of them that forget about interpreting individual neurons. I really don't believe different repetitions of the same training data with different order or different initialization gives you an entirely different network. The only thing which seems to be fixed is the position in information plane. Everything, all the other details is just trying to identify one molecule in this room using thermodynamics. It doesn't make sense. Now, the other thing is, of course, there's highly distributed representation. Most of the relevant information goes through all the neurons in the layers. I cannot say that this is a grandmother cell, and this is a face cell, and this is an eye cell, or something like this. I think this is nonsense. Now, but on the other hand, it tells you why you put an electrode in the auditory cortex, and with very high probability, you see something which responds to your signal, which I always found very strange. I mean, why should it be? Because essentially all the information goes through all the neurons, so all of them respond to your signal, whatever the signal is, in some way or another. Yes, please. You asked already, let him. Alessandro. Just to be fair.
Thank you very much for the amazing talk. I just have a question. So, in a standard network, you are going to apply a linear transformation, which in most cases is invertible, and then some kind of non-linearity, which could be invertible.
No, it's not invertible if you are shrinking the width of the layers. Yeah.
Yes, exactly. So
right.
This is my point. So in a standard network, everything will work even if you keep increasing the size of the layers. And so the way we manage that in our theory is that the weights are considered a stochastic random variable, and therefore the mapping is not deterministic anymore, it's stochastic, and so we actually lose information because of the stochasticity of the weights.
Yes. By the way, it can be almost invertible, it's still stochastic. I mean, it's a frozen stochasticity.
Yes, exactly.
It's what we call quenched randomness. So it's not necessarily not invertible if it's stochastic.
Yes, I completely agree with that.
Right.
So my point is that in our experiments, in our CNNs, in the last layer, let's say in the last 4,000 neurons in the layer, we always have something like, I don't know, 5 kilobytes of information, just because the map is always deterministic. I mean, if the map is deterministic of almost not stochastic, then we have a lot of information in the last layer. So we actually studied the problem from the point of view of the weights.
The last layer.
No, so just we consider the weights to be stochastic just because we need to lose information somewhere. So in your case, where is that you're losing information? Because you are reducing the size of the network?
No, because you are increasing the entropy of the weights. So essentially what happens is that each neuron is getting some relevant information and a lot of noise. From random connections to the irrelevant. Okay. There's no sparsity, I don't cut any connection, right. I don't do anything like this. Well, you can do, but I don't do it here. But
do you consider the weights to be stochastic and part of the map? So the map is
so the map is highly random, but only small part of it is relevant. Now, so essentially essentially neuron gets relevant information plus a lot of irrelevant information, and the signal-to-noise ratio of the noise, signal-to-noise ratio is determining the information capacity.
But when you measure the mutual information between X and T in the MNIST example, you average that over all the possible weights in the posterior?
No.
Or do you
fix
the weights?
I fix the weights, I just average over the inputs.
But then the map is deterministic.
The map is deterministic and still lossy.
I think the source of stochasticity is due to stochastic gradient.
No. There are two things. It's important to understand. There's the dynamics of the training, which is a stochastic process on the weights. Okay, the weights are changing. Now, eventually, you train the network. Everything is fixed. Now you have what I call quenched randomness. I mean, essentially, the weights are random but fixed. And now you put an input, and then you look at what is the signal at a given neuron somewhere, and you see it's mixed out of two things. One of them is the relevant part, and then a lot of noise added to it because there is random connection somewhere in the other parts.
But let's say
the information is determined by the signal-to-noise ratio. Remember that. This is the Gaussian bound on the capacity, and this is if you bound this, you bound information.
But if I have a completely random layer, it still preserves all the information.
Only if you don't change the dimensionality. You're right. Completely random weights will not lose anything. Actually, I have an example of that. I simply don't have time. But we actually did it for layers which have the same width as you want. This is the picture here. So essentially, you see all the layers, they don't start low. Only the last layer starts low. But all the other layers start there and move only along the line at the end. So essentially, they don't lose information, but they compress the representation, eventually. Yeah, you're right. This is the relevant picture for this. Yeah.
Okay, yeah, we consider the weights to be random.
Right. This is the constant width network.
Yeah.
Only the last one is a perceptron at the end. So you see it. But you see that the information in the last one is doing exactly the same story, and all the other layers still compress the representation.
Okay, thank you very much.
Soren?
I'm not sure this is a relevant question, but how much did you say about the distribution of Y? If you, for example, compare problems where you have two labels and they are 50-50 versus
it's an excellent question.
1 in 100.
I need another hour. But essentially, my argument is that deep learning today, trained with cross entropy or log loss, as most people do, is actually good only for stochastic rules. If you really have completely deterministic rules, then in this simplex of the Y, you're going to be pushed to the two corners, and there's absolutely no structure that you can compress. So it's really the noise in the label which allows you to do this refinement. And it's very critical that you have noise in the labels. That's what I argue, but it's a different story. I'm afraid, you're the chair.
One last question.
Very, very quick. If I understood something of your talk,
I hope you did.
I have two implications that I want you to confirm or to deny. First of all, it's better to have fully connected networks, because if you have a sparse connected
everything
network...
I said so far, even in the MNIST data, was fully connected. Some had weight sharing of one way or another and other things, but they're fully connected, yes.
And you claim that it's better to have fully connected because this
claim.
is adding more noise?
I think that sparsity helps, but it's not the reason it generalizes better.
And the other implication is if you have a shallow network, so if I understood your argument, you need an exponential number of units in the shallow network in order to get the same kind of result.
That's true, but I didn't say it.
It's
true,
an implication.
It's true that
It's
you
my
need
implication.
exponential number to express the same function with shallow network. That's a well-known result. I didn't refer to it at all. I'm just talking about the benefit of the hidden layers with the computational benefit. It's somehow reflected, of course.
The dynamics.
Of course, in very wide shallow network, you need exponential time to find the solution. But we didn't study this type of problem.
But then how do you compress information in a shallow network? Only because you have more noise?
I actually argue, I'm talking about deep networks now. Okay, not shallow networks. It's a different story.
Okay, thank you.
Okay.
We need to move on. Let's
Thank
thank Tali one more time.